With animation in Blender, it is often desirable to link motions of different objects together. With an airplane model, a single controller can be used to control the wing's ailerons and the tail's elevator. This allows coordinated movements and eases the animator's workload. Similarly, with a compound bow, the bending of the limbs, rotation of the cams, barrel movement, and string movements all need to be coordinated with drawing of the bowstring. Specifically, we're going to look at the formulas and drivers for coordinating these movements. Blender provides several methods to achieve coordinated movements. Parenting and object constraints allow some limited linking of motions. Keyframes in the timeline provide very precise control, but with several drawbacks. Changing timing of events in the complex timeline can be difficult. Controller motion beyond the keyframes is not extrapolated onto the child objects. A lot of versatility is lost, and animators' workload is significantly increased. The key feature built into Blender to deal with this problem is drivers. A driver allows motion in one object to automatically drive motion in another or multiple other objects or meshes. Drivers can be added to an object through its transform properties, shape key value cells, shader values, or essentially anywhere there is a value key in Blender. If a property box has a dot next to it and takes a numeric entry, it will probably take a driver. For our example, we will use a compound bow model. Specifically, we will look at controlling the cam rotation with pull or draw on the bowstring. Drawing or pulling of the bowstring will be accomplished through a small attached cord called a D-loop. This will move from 1 to 3 meters in our draw cycle along the x-axis with the present scale. We want the cam to rotate from 0 to 120.62 degrees on the z-axis during this cycle. With the cam selected, right mouse click over the Z rotation field and select Add Driver. The field will turn purple, signifying that it has a driver. If you mouse off the driver property box, it will disappear. You can get it back by right mouse clicking over the purple field and selecting Edit Driver. Alternatively, you can select the Open Drivers Editor for a window that will remain open until closed. We will keep the driver as scripted expression. In the red object box, we will select the D-loop with the dropper or the selection box. This is our variable or var. Our time will be x location and space will be local. This means that the D-loop's x location will determine the cam's z rotation. At this point, things don't look too good. Moving our D-loop from 1 to 3 meters gives us cam rotation of 57.296 to 171.89 degrees. Not what we want. This is where the formula in our expression comes into play. The var is the value of our D-loop x location. We have to make this drive our desired cam z rotation. Initially, I'm going to show you the underlying math and the general formula that will give us where we want to go. This can be unpleasant and complicated looking for those who slept through high school algebra. Don't worry, I will follow with a couple of shortcuts and a technique to simplify this formula. We have a variable, the D-loop x location. When it goes from 1 to 3 meters, we want the cam rotation to go from 0 to 120.62 degrees z rotation. If we put these numbers in a graph with the x-axis representing the D-loop location and the y-axis representing the cam rotation, we get a straight line relationship. The formula for this relationship is the slope-intercept formula, y equal mx plus b. M is the slope or angle of the line, and b is the point on the line where it intercepts the zero value x vertical axis. The slope m is equal to y2 minus y1 divided by x2 minus x1, or in this case, 120.62 minus 0 divided by 3 minus 1. The intercept b is equal to y minus mx, using either the initial or final point for x and y. This gives b equal y minus y2 minus y1 divided by x2 minus x1 times x, are using the final point for x and y, b equal 120.62 minus 120.62 minus 0 divided by 3 minus 1 times 3. The whole formula becomes y equal mx plus b equal open parent y2 minus 1 close parent divided by open parent x2 minus x1 close parent times x plus open parent y2 minus open parent y2 minus y1 close parent divided by open parent x2 minus x1 close parent times x2 close parent. In this example, the formula for the blender driver is 120.62 minus 0 divided by 3 minus 1 times var plus 120.62 minus 120.62 minus 0 divided by 3 minus 1 times 3. Oh yeah, Blender also doesn't use degrees and drivers. You have to convert the degrees to radians. This gives us radians, open parent, 120.62 minus 0 divided by 3 minus 1 times var plus 120.62 minus 120.62 minus 0 divided by 3 minus 1 times 3 close parent. If it were location transformation instead of rotation, we would use the first formula. Not very pretty. For many, keyframing in the timeline is starting to look pretty good. There is a couple of steps that will significantly simplify this equation. This process involves normalizing our driving object and applying transforms to deltas for the driven object. Our first step is to apply transforms to deltas on the driven object, in this case the cam. This has to be done previous to adding a driver. Blender has two transform fields. These can be accessed through the Object Properties tab. Select the object, Control A, or select object, and apply transforms or rotations, in this case, to deltas. The main transfer channel will now read 0. The new final Y2 rotation will need to be determined after this action. The new Y1 will now be 0 degrees for the driven object. Normalizing the driver object gives it a value of from 0 to 1. We subtract x1 from the var in the formula and then divide the result by x2 minus x1. This gives us radians open pair var minus x1 divided by x2 minus x1 close parent. We then multiply by y2 minus y1 and add y1. This gives us our new driver formula. Radians open parent var minus x1 divided by x2 minus x1 times y2 minus y1 plus y1 close parent are radians open parent var minus 1 divided by 3 minus 1 times 120.62 minus 0 plus 0 close parent period. The zeros disappear, leaving us with radians open parent var minus x1 divided by x2 minus x1 times y2 close parent, or radians open parent var minus 1 divided by 3 minus 1 times 120.62 close parent. The steps, one more time. 1. Select the object on which the driver will be added, the cam in this instance. Control A and apply the appropriate field to deltas. 2. Determine the initial and final position of the driver, the D loop, x1 and x2. 3. Determine final position of the driven object, y2. 4. Enter driver expression, radians open parent, var minus x1 divided by x2 minus x1 times y2. For rotation, r var minus x1 divided by x2 minus x1 times y2. For translation, this driver can be copied and pasted between objects and the numbers changed as indicated. If the driving object transformation is rotation rather than translation, things get a little more complicated. This is covered in another video. Again, as always, thank you for your attention and thank you for your time.